This time, I'm going to talk about building XGBoost model in Python. XGBoost, which stands for Extreme Gradient Boosting, is a scalable distributed gradient boosted decision tree (GBDT) machine learning library. It is vital to our understanding of XGBoost to first grasp the machine learning concepts and the algorithm that XGBoost builds upon: supervised machine learning, decision tree, ensemble learning, and gradient boosting. The term gradient boosting comes from the idea of boosting or improving a single weak model by combining it with a number of other weak models in order to generate a collectively strong model. Let's go through some key points of XGBoost. First, ensemble learning. XGBoost is ensemble learning methods, meaning it combines the prediction of multiple weak learners, typically decision trees, to create a strong model. In XGBoost, we have multiple weak learners, but all those weak learners are not independent. XGBoost employs a gradient boosting framework, where each weak learner corrects the errors of its predecessor. XGBoost includes regularization terms in its objective function to prevent overfitting. As I mentioned before, XGBoost uses decision trees, and all those decision trees are base learners. And XGBoost has feature importance. XGBoost provides feature importance score, which indicates the contribution of each feature to the model's predictions. This can be useful for feature selection and understanding the model's behavior. And XGBoost has parallelization, cross-validation. XGBoost is versatile and can be applied to a variety of machine learning tasks, including classification, regression, ranking, and user-defined objective functions. For XGBoost, we have a library we can use, but in this video, I'm going to use the code from scratch and compare the result from the library. In this video, I'm going to use the California housing dataset as my data. You can find the definition of this California housing dataset definition on this website. And it will show you the number of instances, number of attributes, and the attribute information. Please note this dataset doesn't provide the data for individual house, but it will provide the average value of the houses in a block group. So it will give you the median income in block group and also the median house age in block group and average number of rooms per household and average number of bedroom per household, etc. This is the Python code for my model. It is pretty long, but the structure is quite simple. We have a class called XGBoost model here, and then we have a class XGBooster here. And this is a model written from the scratch. I'm going to use this model, and then I will import the XGBoost model from the library and run the model from the library and compare the results. First, let's take a look at this XGBooster class. The class XGBooster represents a decision tree used in gradient boosting, particularly tailored for the XGBoost algorithm. First, it has initialization here, and then it's the tree building. Maybe insert child nodes method is a private method. It is responsible for recursively building the tree by finding the best splits. And we have a function finding best split. It will find the best split for a given feature. It sorts the data points based on the feature, iterates through the sorted data points, and calculates the gain for each possible split. Of course, this gain is the improvement in the loss function, and then it updates best score so far, split feature, and threshold. And for this recursive prediction, we have this predict row method. It recursively traverses the tree to make prediction for a given row. Now, let's take a look at the fit function in class XGBoost model. The fit function is an implementation of the training process for a gradient boosting model. First, it has initialization here, and then it iterates through the specified number of boosting rounds. For my model, I use 50 as the number of boosting rounds. And then inside this loop, it will compute the gradients and hastens of the loss function with respect to the current predictions using the provided objective object. You can see I'm calculating gradients and hastens here, and then optionally subsamples the data if self-subsample is less than 1.0 here. It creates a new boosting model, a tree, using the XGBooster class with the input features x, gradients, hastens, and other parameters. You see, it will create a tree booster class, which I explained before here. And it updates the current prediction by adding the product of learning rates and predictions of the newly created booster. You can see it updated here, and then it appends the booster to the list of boosters here. This code represents a basic gradient boosting training loop. The boosting process involves iteratively adding weak learners or trees to the ensemble, where each new tree is trained to correct the errors of the combined predictions of the existing ensemble. The objective object encapsulates the loss function, and the training process aims to minimize this loss. Now, let's run our model. You see, first, it displays the data set we are using for our model, and then it will start our training process. As I mentioned before, I will run it for 50 times. I will upload this model to my GitHub so you can download it and run it by yourself. Of course, you can change all those parameters, including this number of boost round, and see what will happen if you use your own parameters. Now we finish our training. You can see the loss function start with 3.17 and it decreases until it gets a value 0.24. And if we draw it in a graph, the training loss look like this. It will keep decrease when we train our model. For one data point, you can see when we train our model, the gradient is getting close to 0. And when we use the model from the scratch, it has the score 0.2434, and if we use a library, it has the value 0.2412. You can see the value is very close. This is how you can build your XGBoost model from scratch in Python. Please comment, like, and subscribe to my YouTube channel. Thank you so much for watching.